I see the cosmos and I marvel. That's why I pursue fundamental physics, the deepest laws, forces, and particles that construct the cosmos. But why do these all work so well? Start with what we know. Science has discovered the strengths of forces like gravity and electromagnetism, and the description of particles such as their masses. All these strengths and descriptions are defined with numbers. These numbers are the constants of nature, and the big question is, why are the constants of nature seemingly ideal to make a cosmos? Are all these seemingly ideal constants accidents? And why did they just happen to work together to generate structures? Galaxies, stars, planets, people. Is all this what's called fine-tuning? What's fine-tuning in physics? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. What is fine-tuning's actual claim? And how does it relate to conditions that allow for complex structures to develop, including human beings? I've been, well, a bit obsessed with fine-tuning. Is it a clue? Is it a mirage? How might it work? What could it mean? That's why, when I heard about the Physics of Fine-Tuning conference to be held in Crete, Greece, I made plans to attend. The magnificence of the setting, elements flowing together, is this too a kind of fine-tuning? I mustn't lose myself imagining effects driving causes. I'd best be careful, rational, rely on science. I begin with one of the pioneers of fine-tuning, editor of the classic work Universe or Multiverse, Bernard Carr. Bernard, I've been following fine-tuning for many decades as a real potential probe of the nature of reality. I'd love you to give me the history of your involvement in fine-tuning.
Maybe I should just start off by saying mankind started with the anthropocentric view, which says that man is the center of the universe. And of course, that idea was demolished, and we found that the Earth wasn't the center of the universe at all. And more importantly, Newton developed the idea of a mechanistic universe in which the laws of nature more or less continue, oblivious to whether there's anybody observing the world at all. And from that perspective, the observer became completely unimportant. But then in the 20th century, they developed what has become called the anthropic principle, which says that actually certain features of the universe seem to have to be the way they are, because otherwise life, or at least an observer, couldn't be here to ask questions about it. This question came out of physics and cosmology, not just from philosophy. I suppose the crucial paper was probably in 1974, when Bernard Carr pointed out the existence of these extraordinary coincidences involving the constants of physics, which seemed to be necessary to have observers in the universe. And indeed, it was Carter who coined the term anthropic, which is actually a rather bad term. I mean, I think he regrets it now, because it comes from the Greek word anthropos, which means man, but actually these tunings clearly aren't anything to do with humans in particular. They're to do with the evolution of maybe complexity in the universe. And then I came into the story, I think, in about 1979, when myself and Martin Rees wrote a paper which was published in Nature. And this was, I suppose, the first paper to give a broad overview of all the various coincidences which seem to be necessary for life. One of the points of our paper was that actually most of the scales of structures which exist in the universe, all the way from the very smallest to people to planets to stars to galaxies to the universe itself, those scales of structure depend upon a few basic dimensionless constants which arise in physics. And because of that, you automatically find there are certain surprising coincidences, if you like, between these different scales of structure. And just to give a simple example, the size of a human being is essentially the geometric mean of the Planck scale, the smallest scale that could ever exist, 10 to the minus 33 centimeters, and the scale of the observable universe, which is 10 to the 27 centimeters. Now, at first you might think, well, that's remarkable, that's full of mystical significance, where the geometric mean of the smallest and the largest, but actually it's not. It was just a result of straightforward physics. Then there are coincidences which involve what is sometimes called the weak anthropic principle. Now, the weak anthropic principle says, given the constants of nature, there is a selection effect on when and where we observe the universe. And I suppose the most famous of these weak anthropic coincidences involves the question of the age of the universe. And because we know the universe it's 14 billion years old, and so the size of the universe is 14 billion light years. So you might say, well, why is the universe so enormous? You might just say, well, it just happens that the universe is 14, let's say 10 billion years old, to be more rough. Now, in order to have observers in the universe, you have to have carbon, and those elements have to be made in stars, which then explode, and it requires a certain time for those stars to go through their nuclear burning. Now, the main sequence time of a star like the sun is about roughly 10 billion years. So you have to wait 10 billion years in order to have any elements around for us to be here. On the other hand, if you waited much longer than that, there would be no stars left. And so there's a little window of time in which observers are bound to be here. And it's not saying the universe doesn't exist outside this little window of time. It's just saying that if you're observing the universe, you expect it to be something like 10 billion years old. Right. And really, that's just a matter of logic.
Now, how do you get fine-tuning in there?
That particular coincidence, as I said, it doesn't particularly require a fine-tuning. But actually, if you then ask what is the age of the universe, that depends on an important parameter, what's called the gravitational coupling constant, which is a very small number which determines the strength of gravity. So actually, it turns out that this weak anthropic constraint on the age of the universe is also a constraint on the value of the gravitational fine structure constant, which is this tiny value of about 10 to the minus 40. This was the weak anthropic principle. Far more challenging was the realization that there are relationships between the physical constants themselves which seem to be necessary for us to be here. One such coincidence is the fact that you need to have stars which are both convective and radiative in their outer envelopes. That's to say, the heat generated in the core can get to the surface by radiative processes or convective processes. That only happens around a critical mass. And that critical mass is in the mass range in which stars actually exist, only because of a remarkable tuning between the gravitational fine structure constant, which is this tiny value of 10 to the minus 40, and the electrical fine structure constant, which is called the fine structure constant, which is roughly 10 to the minus 2. It's 1 over 137. It turns out that the reason we have both these types of stars is only because of this remarkable tuning, that the gravitational fine structure constant is the 20th power of the electric fine structure constant.
So since your seminal 1979 paper on fine-tuning, what has been sort of the sociological history of fine-tuning in the physics community?
Originally, the paper was met with a lot of skepticism. It seemed too philosophical, almost theological in its nature, and people felt it was not really proper science. But since then, there have been changes. In particular, physicists themselves produced the idea of the multiverse, the idea that our universe might just be one of a whole ensemble of universes in which the constants were different. And that very naturally would explain why there can be a selection effect. Because if there were many, many universes, we would have to be, by necessity, in the universe which had the constants required for us to be here. And I think that was quite important in the history of the subject, because it did show that actually, a lot of eminent scientists take this subject seriously enough that it's a serious scientific question which can be addressed in a respectable way.
So, fine-tuning is the claim that conditions that allow for complex structures to develop, including human beings, depend on a few fundamental constants of nature staying within certain ranges of values. And if these fundamental constants were to change much, structures couldn't exist. we couldn't exist. What's interesting is that fine-tuning in physics began to be accepted as legitimate science only after there came a natural mechanism for its generation. Multiple universes, each universe with a different tune, as it were, and only in those universes where the tuning was fine could creatures emerge to wonder why there was fine-tuning. Without multiple universes to do the fine-tuning, well, one might need a fine-tuner. And to many scientists, a fine-tuner, sometimes known as God, just wouldn't do. But how robust is the claim of fine-tuning? How to test its strength? One way is to catalog the candidates for fine-tuning. Which constants of nature might qualify? I meet the co-author of a book on precisely this topic, A Fortunate Universe, Life in a Finely Tuned Cosmos, cosmologist Luke Barnes.
I think there's been a realization that some of the big problems in physics have turned out to be kind of fine-tuning problems. So, for example, in particle physics, there's this problem called the hierarchy problem, that some of the masses of the particles seem to be unusually small, and we're not entirely sure why. And that's kind of a fine-tuning problem. If I change this number a little bit, then some rather drastic results happen. And so once you've realized that, actually fine-tuning this idea that these numbers that we don't quite know why they are what they are, and they have drastic consequences, is now a problem you start to see in more places in physics.
Let's go through the different categories of fine-tuning. How would you define that?
The thing that binds them all together, first of all, the unity, is there are these numbers in physics, we don't know why they are what they are. And then within those, there's sort of two categories. There's the fundamental properties of the universe, so that's particles, masses, forces, those sorts of things. And then there's what you might categorize under initial conditions of the cosmos. So how fast is it expanding, what's it full of, the cosmological constant. And there are interesting cases of fine-tuning in each. There are various ways where if you change these numbers, you can make disasters for life. When you think of it as a physicist, between what's there in the equations that determine how the universe moves and changes and how did the universe start off? So both of those have to sort of come together to produce the universe as we see it. When you sort of boil physics down to its basic elements, you have an equation, you have some numbers in the equation, you have some numbers that describe the specific universe that we think we live in, and those are the numbers that we can't currently explain, just because that's where our physics currently stops.
First principles.
Yeah.
What's the order of magnitude of amount of numbers we're talking about in physics? There are, what, 26 or so?
Yeah, there's 26 in what's called the standard model of particle physics, and then the standard cosmological model is about 6 more numbers that tell you how the universe starts and how it evolves, and one more to say where we are in the sort of history of the cosmos.
Of the cosmological fine-tuned numbers, give me some examples.
So one of them would be how much matter is there, dark matter and ordinary matter, for every sort of photon, every particle of light in the universe.
What is that number?
For ordinary matter, it's 1 proton per billion photons,
okay.
roughly. And then there's about 6 times as much dark matter as ordinary matter. Okay. And then there's the cosmological constant. So if you turn that into a form of energy, we call it dark energy, there's about twice or a bit more than twice as much energy as there is energy in matter, dark and ordinary matter.
Right. And each of these are subject to a fine-tuning analysis.
Yeah, each of them we can say what would happen if I changed this number. And in some of them, to be honest, not much changes, but there are probably about 10 of them where within the total range that the theory allows for these numbers, some disasters happen for life if you change the numbers by too much.
And not just for life, but it'd be for structure in general.
Yeah, so we would love to start with the basic equations we have and sort of derive what would happen for life on a planet. Unfortunately, we can't do that, but what we can say is when structure in the universe would fail to form. So one of the most convincing cases for the particle physics numbers is when will I not have them stick together to make a nuclei and atoms? Right. So if you don't make those, you probably don't make any of the bigger things.
Right. In terms of your feelings today, as you've followed fine-tuning, do you sense a trend?
Yeah, I think there's been a trend towards taking these things more seriously. A lot more of the heavy machinery of theoretical physics is being aimed at these problems. Better models of stars, better models of galaxy formation. On the particle physics side, more sophisticated models of how particle physics comes together. For the most part, we're seeing in more and more detail just what happens when you change these numbers.
Here's the landscape of fine-tuning. In the standard model of particle physics, 26 numbers describing nuclear and atomic reactions. In the standard model of cosmology, 6 to 8 numbers describing the formation and evolution of the universe. Is fine-tuning then a profound change in how physics is done, visualizing laws and constants through the lens of fine-tuning? And not only what they are in our universe, but also what they could be in other universes? Fine-tuning energizes me. Is it that clue? Can it push for purpose? Then I worry. Might fine-tuning subvert the Copernican insight that human beings are not the center of the universe? I speak with an astrophysicist who insists that science must test theories by real-world observations and experiments. The chair of Harvard's Department of Astronomy, Avi Loeb.
My personal view is that we are byproducts, accidental byproducts. We are not too significant in the cosmic scheme of things. So here we are, creatures on the surface of a habitable planet, 1 out of 10 to the power 20 in the universe. We live for a short time. Matter takes its shape in the form of our bodies. This is matter that was expelled from the heart of a massive star in a supernova explosion. So we owe our existence to many things that happen in the universe since the Big Bang. But we are just transient structures passing by with no great significance. And obviously, if the conditions were different, we wouldn't be the way we are. I don't think there was any particular fine-tuning. In fact, you might ask, there is a lot of dark matter out there. You might think, this amount of dark matter is actually necessary for galaxies like the Milky Way to exist, because if there was no dark matter, there would be no galaxies, since the cosmic microwave background has no non-uniformities on small scales of the scale of a galaxy. And early on, the ordinary matter was coupled to the radiation that fills the universe. So there would be no inhomogeneities, no clumps in the universe on the scale of galaxies from which stars like the sun would form. So you might say dark matter is necessary in order for us to exist. But there may be a specific reason why dark matter is there, which is it's a particular particle that has some particular properties, just like ordinary matter, and it happens to have the abundance that it does. And we are a byproduct of that. So there was no fine-tuning necessary for us to exist. It's just that these are the way things are.
Does that way of thinking help a physicist or an astronomer or cosmologist advance their way of thinking in terms of future discoveries?
As long as this line of thinking is real, in the sense that indeed these other possibilities are realized somewhere else, maybe in other parts of the multiverse, if that's the case, then it helps. If that's not the case, then we are just illusioned in thinking so. And the key of science is to have testable predictions. And the only way to find out is by having data. From reality out there, we could live in a theory bubble where we think we know the truth. But just like the housing bubble, it might be completely fictitious, where our ideas have nothing to do with reality. And the real estate of science, which is talking about reality, may be completely overvalued in our theory bubble with no real reference to the truth. And in my view, we should explore ideas as long as they are testable. And so the key is to find ways by which observations or experiments can test the idea of fine-tuning.
Avi offers a more minimalist view of fine-tuning, more apparent and essential, he says, a brute fact of nature that things are as they are, without meaning, offering no clues. I'd have hoped reality were more, with some kind of meaning, offering clues galore. But reality is what reality is, and my hope won't change it. Still, I pursue my hope with a more maximalist view of fine-tuning. Attending the Crete conference is a distinguished cosmologist who is not reticent both to question the multiverse and to seek purpose in the cosmos. George Ellis. George, we're here in Crete, conference Physics of Fine-Tuning. In the past, it's been philosophers and those scientists who engaged in the science-religion discussion. You've kind of existed in all these worlds. So what's your view? What's happening here?
I think it's become apparent to a lot of, as you say, mainstream cosmologists that there are interesting questions to be asked here. For instance, what are the kinds of conditions which will lead to a stellar system with habitable planets? Probably you want planets with water, and that happens only at certain distances from the central star and so on. And of course, a lot of the driving of this is to some extent given by the huge number of extrasolar planets which have now been found, which kind of has driven the attention of astronomers onto the question of life in the universe.
You've actually wanted to extend the concept of fine-tuning into biology.
Yes. So most of the fine-tuning has been what variation of the physics parameters would allow galaxies to exist, stars to exist, planets to exist on the one hand. Secondly, heavy elements like carbon, nitrogen, oxygen, phosphorus, which are crucial to our existence as physical beings. And then water and planets with water. But none of that actually gets to life itself. Now, for life itself, I'm a carbonist. I believe that life is based in carbon for a whole lot of reasons. And you have to have a whole lot of stuff for life itself to come into existence. And this is the link between physics, chemistry, and biochemistry. And the key thing is what enables biomolecules exist. And there's two really important biomolecules. The one is DNA and RNA. The ones which are, in a sense, much more important are the proteins. And in fact, the proteins are the ones that actually do the work. The question is, if you shift the fine structure constant, DNA winds up on itself in a certain pattern. Will you destroy that ability to wind up and those matchings to take place? That's one kind of question.
And
the fine structure constant.
Fine structure constant is?
Well, roughly, it's the strength of the electromagnetic force. Okay. And then the ratio of the electron to the proton mass is another one which comes in and affects these, because these affects the shapes of molecules. And then the second one is a huge amount of stuff which goes on in biology, the lock and key mechanism of biology, where molecules fit together and cause conformations to change and so on. And in particular, the brain is based on voltage-gated ion channels. And in those ion channels, when the voltage changes, it lets ions through, and it doesn't. Right. The question is, if you shift the fine structure constant or the electron-proton ratio, will that stuff still work?
Right. What you're doing is you're using some of the exact same information in terms of weight ratios between proton and electron, or the strength of the electromagnetic.
We're using the Schrödinger equation in detail for molecules.
Right. But if here the same kind of fine-tuning has to work in two radically different areas, that significantly strengthens the philosophical implications of what that means.
Yeah, I agree with that.
Okay, because I'm not sure I agree with that, and because I'm not sure if the data would hold that. But what you're saying in biology, even if the biological limits were wider, it's still a limit.
Yeah, but it's a rather disturbing limit, because it's saying in some sense that the laws of physics had the foreknowledge of biology written into it, and that's a rather strange kind of statement.
Strange indeed, beautiful too, the laws of physics, but fine-tuned not only to generate galaxies, stars, planets, but also to sprout life and mind. No matter one's views, whether fine-tuning is real and relevant or brute fact and trivial, fine-tuning makes you think. Some criticize fine-tuning for reaching grandiose metaphysical conclusions. I fear grandiosity. Fine-tuning in physics to me requires one of three possibilities, each of them crucial for understanding the cosmos. 1. Necessity. Only one way is possible. The laws of physics are fixed and unchangeable, and they just happen to generate life. 2. Multiplicity. Every way is possible. Immense numbers of universes ensure that anything that can happen will happen, including us. 3. Meaning or purpose. There is more to the universe than the laws of physics, whatever more might mean. I marvel that the foundations of the cosmos can be reduced to three possibilities. For me, for now, that's good enough. Fine-tuning has brought me a little closer to truth.
For complete interviews and for further information, please visit closertotruth.com.